All right, now we're going to deal with work energy theorem, and we've been alluding to this all unit long. Work, check out this definition, is the amount of energy expended to displace an object exerting a force, but it is the amount of energy. And energy is the ability to do work. So energy is all about doing work, and work is all about spending energy. Work and energy are the exact same thing. They use the same unit. Both use the units of joules. They are the same thing. So if you do work on an object, you push it, right, over some displacement, but you push it, well, that object is going to speed up. So what we can say is the amount of work you do pushing whatever this object is causes it to gain velocity, aka it causes a change in kinetic energy. Now be very careful with that change in kinetic energy. That's not just 1/2 mv squared, it's change in kinetic energy, kind of like we had with change in momentum. So this is going to work out to be 1/2 m delta v squared, final velocity minus initial velocity, all in parentheses with a square outside of that. Vice versa is true also. If an object does work on itself, or if an object does some work, it can raise itself to a new height. So if a rocket, let's say, does work, and we're going to have a problem like that. If a rocket does work, so it is exerting a force over displacement coming upwards, it can gain gravitational potential energy, if we're dealing specifically with gravitational potential in this case. And of course, using the same rocket example, let's say it's already orbiting. If gravity does work on the rocket, so now it's not the rocket doing work, it's gravity doing work on the rocket, applying a force back down over some displacement, the rocket is going to gain velocity as it comes back down. Really, the one thing that you need to think of in all of these problems, and what we were trying to lead you into thinking about in the conservation of energy section, is not blindly following what some people would call the conservation of energy equation, and that would be incorrect. The 1/2 mv squared plus mgh equals 1/2 mv squared plus mgh, because the conservation of energy equation is just energy initial equals energy final. And so the questions you need to ask yourself, because we're not just now living in a world where it's just kinetic into potential or potential into kinetic and you can follow that equation blindly. You need to actually ask, where is the energy coming from? Set everything that the energy is coming from as your initial, and then where is the energy going? And set everything where the energy is going into as your final amount of energy. So if the energy is coming from, like in this problem, let's say a car's engine exerting a force over displacement, well, where is the energy coming from? It's the work done by the car engine. So I would put work over here on the initial side. Where is the energy going? It's going into trying to cause the car to speed up. So I'd put change in kinetic energy over here, right? Other ways you can look at this. Let's say the car already had a velocity here. Where is the energy coming from? Well, it's coming from the car's engine, so I would put a work done by the car's engine, and it already has a velocity, so I'd have work plus kinetic energy, initial kinetic energy, equals, what is it going into? It's going in to try to make it speed up even more. So I'd put kinetic energy on the other side and solve for my final velocity. So once again, the trick is ask where's energy coming from, put everything where it's coming from or what energy it already has as the initial, and where is the energy going? Put that as your final. Let's actually do that car problem now. We have a car, has a mass of 1,000 kilograms, and the engine of this car is able to provide a maximum force of 10,000 newtons. By the way, this is the mass of the car, not the mass of just the car's engine. So 10,000 newtons to accelerate it for 20 meters. And if the engine provides 10,000 newtons for 20 meters, how fast does that car end up going? So I drew a quick picture, and I created my variable bank, pulling everything out there. Be careful of significant figures up here. We'll talk about that at the end, going back to the original to determine how many sig figs I get. Looking at my variable bank and thinking through this problem, where is the energy coming from? The energy is coming from the work done by the car's engine. The car's engine actually does some work, and where is that energy going into? Because those are the two questions, right? Where is the energy coming from? It's coming from the car's engine. The car's engine is doing work. Where is it going into? It's trying to make the car speed up, change in kinetic energy. Now, please don't get confused by notation. That is a subscript just to try to point out this is work done by the car's engine. So subscripts we just simply use for notation. That's not an actual variable. You could have also, if you had so chosen, not even put in change in kinetic energy. If you were thinking initial amount of energy and final amount of energy, the initial amount of energy is just the work done, and the final amount of energy would just be the final kinetic energy, because the car has an initial velocity of 0, meaning it has no initial kinetic energy. If it did have some initial kinetic energy, then you would add a kinetic energy onto the initial side in that case. I'm going to actually solve it, though, where all the work goes into causing a change in kinetic energy, so a 1/2 m delta v squared on this side. So now I'm going to break these two down into their two equations that we know. Work is force times displacement, and kinetic energy 1/2 mv squared. So now I have force times displacement 1/2 m delta v squared, delta because it's a change in kinetic energy. Since we aren't going to be changing the mass of this object or the car, it's a change in velocity, which breaks into final minus initial. Now be very careful here, you don't do a math blunder. This square is on the outside, so it has to stay outside the parentheses here. That is not the same thing as VF squared minus VI squared. That is very different because it's this entire thing multiplied by itself. Well, now looking at my variable bank and looking at my equation, I know everything to begin to substitute in. So after substituting in, that leaves me with my only one variable, VF, so now I can begin to work the algebra. Remember, anything minus 0 is itself, so this is just going to turn out to be VF. Remember, I'm trying to peel things away from my variable, so I divide both sides by 500, and then square root both sides. And the final velocity of this car turns out to be 20.0 meters per second. 20.0 because check sig figs here. This has 4, this has 5. Notice the decimal at the very end making those trailing zeros count. And this has 3, so the least number of significant figures, 3 here, so 20.0 meters per second. Once again, the trick with all energy problems, including work energy problems, because work and energy are the same thing, so it's still just a conservation of energy problem. The trick is to simply ask, where is the energy coming from? Where is it going into? One last problem I want to solve. A rocket is going to be launched skyward. I give you the mass and the thrust that the engine is able to exert, and the rocket needs to get up to 100 kilometers above the Earth's surface to where we're actually into the edge of space. So how far must the rocket's engine burn to actually get it up there? Because if you think about it, a rocket's engine doesn't have to burn all 100 kilometers. It's going to accelerate while the rocket's engine is burning, and then after it stops accelerating, it doesn't instantly come to a stop. It coasts. It's actually decelerating on the way up. Gravity slowing it down, but we'll call it coasting, all the way up to the last to 100 meters. So what distance does the rocket engine actually have to burn? Now, whenever you're working these problems, be very, very careful. Here, if you think about this, where's the energy coming from? The energy is coming from the rocket's engine. So the rocket's engines burn the entire time coming up. So work done by the rocket's engines. Where does the energy go into? Gravitational potential. It's trying to cause the rocket to go up. So I'm going to have work done by the rocket's engines equals change in gravitational potential energy. But I need to be careful to keep the displacement that the rocket's engines is burning over and the height, which is the 100 kilometers, separate, because those are two separate things. All right, so making my variable bank, I already see something that I might need to change. I actually could leave this as 100 kilometers, but just out of good habit, because everything would cancel out, giving me a displacement in kilometers also, but just out of good habits, I'm going to convert my kilometers back to meters. Now I'm actually ready to think about energy here. Where's the energy coming from? Well, it's all the work done by the engine. And where is that energy going into? It's going into a change in gravitational potential energy. And I know the equations for work, and I know the equation for gravitational potential energy. Change here because of a change in height. We should point out that the initial height is 0 because we're starting out at ground level. So that's going to end up subtracting out. So now, whenever I'm looking at this, I know everything. I do need to go ahead, I guess, in the next line and actually make this mg in the delta h is going to be the final height minus the initial height. And I know what the final height and the initial height is. The initial height is 0. We're starting at ground level. And the final height is I need to get up to 100 kilometers or 100,000 meters here. And the displacement, how far the rocket's engines have to burn, that's the amount of, that's the distance that the work is being done over, is what I'm looking for. Now I'm ready to just go ahead and plug in numbers and work the algebra. Multiplying the entire right side together, because there are no variables over there, I come out with 4.1202 times 10 to the 10th. And now, trying to solve for the displacement, I'm going to divide both sides by 1,050,000. I come out with 39,240 meters. Coming back up to look at my significant figures, I'm going to come back into my problem and put a decimal right there, if that's okay, for 100 kilometers. That'll give me 3 sig figs, limiting me here with this number to 2 significant figures. Meaning it turned out that the rockets have to burn for 39,000 meters. In kilometers, that's 39 kilometers approximately. So of the amount of distance, the distance that you actually have to burn your rockets is just 39, kilometers, km of the 100 kilometers, meaning that you build up enough speed in this part that you can coast for a very, very long ways, actually the majority of it, all the way up to your 100-kilometer height for this rocket. Once again, the point of emphasis for all these energy problems, especially these work energy theorem problems, is you need to ask, where is the energy coming from and where is it going into? Put all the things that the energy is coming from, or what type of energy it has in the beginning as the initial, and put all of the types of energy that it is going into the final side, and then go ahead and solve.